Each of us has seen a door at some point in our lives. It may even be one without a traditional door panel, just a simple entrance. However, the door we will talk about now has never been seen by anyone living today, and even the greatest minds of humanity do not know for certain where it leads. There are many such mysterious openings, possibly far more than we can imagine. Do the traditional epithets of black, cold, and infinite fit this incomprehensible entrance to other worlds? Nikodem Poplavsky, a scientist from the American University of New Haven, came to a stunning conclusion that not only overturns our understanding of the familiar world as a whole, but also uproots the most sacred beliefs of many of our followers and science enthusiasts. Einstein's elegant theories and the legendary scientist's formula crumble like a poorly constructed card house, and the concepts introduced become a meaningless set of numbers and letters. How dare Poplavsky encroach on eternal astrophysical postulates? This once again proves the truth of the well-known rule about two people who know that a certain process is impossible, and a third who does not know this and therefore makes a discovery. Therefore, scientists in the United States dared to suggest that our entire world's planets, galaxies, and the universe as a whole is located in a kind of vestibule between two worlds in a tunnel between a black and a white hole. Skeptical listeners will ask about the mechanism of this unimaginable process. According to the theory of the aforementioned scientist, who was supported by another well-known figure in the world of science, Michael Finkel, to understand how personal black holes appeared in humanity, we must go back 14 billion years to the moment of the birth of our universe. According to Poplavsky, the main mistake lies in the interpretation of the origin of the universe. Scientists believe that the concept of singularity as a point with infinite density and infinitely small dimensions does not exist, and this completely contradicts Einstein's formula, in which singularity is a mandatory condition. In reality, the object from which everything hypothetically originated had a finite size, although it was trillions of times smaller than any known object. This compressed seed gave rise to a massive force known as the Big Bang, while being inside a black hole. Black holes are mysterious objects that we can only observe indirectly. Essentially, they are the corpses of giant stars, inside one of which, according to some physicists, our world exists. Unlike the ephemeral singularities, an American physicist believes that finite processes occur in the depths of the black monster, compressing a certain point to small but finite sizes, the same seed that weighs trillions of stars and is many trillion times smaller than an atom. It is not infinite, and in fact, according to the scientist, there exists an immensely heavy object that is located in every black hole. Under the influence of certain forces and lightning-fast rotation, it periodically bursts out spectacularly, freeing itself from the annoying shell, like a spring relieved of pressure. Exiting the black tunnel, a white hole may exist beyond which an absolutely different world exists. How many of such formations there are in the universe is unknown to anyone, as the human mind struggles to even comprehend the possibilities of such events. The incredible theory of Poplavsky and Finkel, instantly picked up by the famous scientific magazine National Geographic, was investigated, and a report by physicists was published in it. It was claimed that black holes are furnaces in which everything is forged. It may sound a bit pompous, but what the scientist meant was the following. 14 billion years ago, a massive explosion occurred inside a black hole due to processes within the dark monster's belly, triggering the formation of our world. The explosion was so powerful that creating any particle that would later give rise to planets, stars, and galaxies was no challenge for it, and there may be infinite such seeds. By the way, this unusual theory explains some discrepancies between the laws of the universe and scientific data, such as visible neutrino oscillations, quantum paradoxes, the presence of dark energy in matter. In other words, what we are used to considering deadly and destructive is our home, and proving this theory is a long and arduous path, but it may contain a grain of truth. After all, a ladybug crawling inside a sphere is also completely confident that the surface is perfectly flat and unshakable. Once, the famous astrophysicist Neil deGrasse Tyson cheerfully said that if a black hole were to visit our solar system, it would be a bad day. After all, there is nothing worse than the ability to break down into atoms, but we are used to thinking that black holes are somewhere far away in other parts of the universe. But what if one of them literally appears on our doorstep? What will happen if an uninvited guest the size of 1 millimeter settles on our Earth? Physicists asked a similar question in 2008 when the Large Hadron Collider was launched. At that time, many scientists, including Stephen Hawking, were afraid that this greatest invention of humanity could create many microscopic black holes that would engulf everything around us and we would cease to exist forever. Moreover, these were not the only problems predicted by the opponents of the collider. However, more than 10 years have passed since then, and if you are watching this video, it means that the Large Hadron Collider is working quietly on its own and does not pose any dangers capable of destroying the Earth. In fact, to create a mini black hole, you would need 10 to the power of 15 times more energy than the Large Hadron Collider can handle. But even if we manage to use such a huge amount of energy to create a micro black hole, we would need to work with the fourth dimension in space, which is not particularly well studied or understood in this context. But let's suppose that we miraculously managed to create a microscopic black hole in our limited universe. It was possible to create a microscopic black hole in our limited and pathetic 3D world. I rush to disappoint those who are eagerly awaiting the apocalypse. It must be postponed for some time, because in this case, the mini black hole is likely to evaporate instantly due to the so-called Hawking radiation. After all, black holes not only absorb energy, but also emit it, thereby posing no threat to the Large Hadron Collider, at least for now, until we learn to use a large amount of energy and fully explore the fourth dimension in space. Nevertheless, microscopic black holes can arise even without the Large Hadron Collider, since billions of black holes now permeate our planet. So, are we doomed, and will the Earth soon be torn into small pieces by mysterious cosmic objects? Relax, it's not that bad, at least not now. After all, our multi-million army of black holes has been attacking our home planet for billions of years. At the same time, the individual mass of a black hole's absorption can reach up to 100 tons, but their size does not exceed that of an atom. The diameter corresponds to a small event horizon, a hypothetical line beyond which space and time curve and matter begins to be absorbed and torn apart into atoms. For this reason, a mini black hole cannot even swallow bacteria on our dinner table. But even if it were to start feeding on our planet, it would take a very long time, actually several billion years, by which time humanity would likely have gone extinct. Otherwise, it could have found another place to live in the universe. However, there is one thing: if the diameter of many black holes were to increase to the size visible to the naked eye, events would be completely different. We won't confuse your brain with complex calculations and the strange world of higher physics, but according to calculations, a black hole with a diameter of 1 millimeter will have a mass of more than 5 lunar masses, which is about 11% of the mass of the Earth. The scale of the black hole's influence depends on where it is located on the surface of the Earth at the center of the planet, or for example, in the room of a guy you hate. Assuming that the 1 millimeter black monster is located on the surface of the Earth, the sphere of influence of the black hole is about 1/3 the radius of the Earth, or about 1,320 miles, 2,124 kilometers, which will lead to a noticeable increase in the overall gravity of the Earth, which in turn will affect the orbit of the Moon. It will be deflected from its current course and begin moving along an elliptical orbit. But if the Moon only changes its course and survives, another even more terrifying fate awaits us and all matter in close proximity to this monster. If we were nearby, we would be torn apart, and it would happen so quickly that we wouldn't even have time to blink. By settling with us, the black hole will deliberately move towards the center of the Earth, and nothing and no one will be able to stop it. Without any obstacles, it could consume everything and reach the center of the Earth in just 42 minutes. Insatiable monsters passing through the Earth's core would reach the other side of the surface at about the same time. But the black hole doesn't just stop there. If its relative speed is at least 12 kilometers per second, it will orbit around the Earth along with its sphere of gravitational influence. With each orbit, the Earth loses its mass, and thus the black hole begins its consumption by devouring the crust and a large part of the mantle. This means our complete destruction and the destruction of all life on the surface of the Earth. But before it devours all living things, the black hole will smooth out the corners, seemingly. It was possible to create a microscopic black hole in our limited and pitiful 3D world, but I am sorry to disappoint those who are eagerly waiting for the apocalypse. It should be postponed for some time because in this case, the mini black hole is most likely to evaporate instantly due to the so-called Hawking radiation. Black holes not only absorb energy but also emit it, so a Large Hadron Collider does not threaten us, at least for now, until we learn to use a large amount of energy and fully explore the fourth dimension in space. Nevertheless, microscopic black holes can arise even without a Large Hadron Collider. The point is that billions of black holes penetrate our planet, and what is happening is that we are doomed, and the Earth will soon be torn to pieces by mysterious cosmic objects. Relax, it's not that bad, at least not now. After all, our multi-million army of black holes has been attacking our native planet for billions of years. At the same time, the individual mass of a black hole absorption can reach up to 100 tons, but their size does not exceed the atom. Such a small diameter accordingly creates a small event horizon, a hypothetical line beyond which there is no return, and everything falls into the black hole. But before the black hole devours all living things, it smooths out the corners, apparently to make it easier to eat. Gas will twist into a gravitational spiral, like sugar when making cotton candy, and our planet will simply turn into a broken disk of hot stone. The material from the formed disk will produce a lot of heat, and it is assumed that it will have a temperature of about 6,000 Kelvin, roughly like the Earth's core or the surface of the Sun. Because the disk will emit as if it were giving off black holes, it would be an amazing and at the same time frightening sight, because like a vampire, the black hole would suck the shine of its energy from the planet. Scientists believe that to complete the chaos, there will be no place for life, which will simply become impossible, leading to frequent collisions within the solar system for 1,000,000 years. This is just a terrible theory at the moment, but it is still far from us. In any case, in 5 billion years, humanity can start building an ark and move to some other planet, maybe even in another galaxy, because it is far from a fact that the solar system can survive for that long. But for now, you can safely let billions of non-black holes penetrate you without fear of atomic hacking, although it will look impressive. A basic education is no longer a luxury, as anyone who wants it can get it. Therefore, there are probably very few people left on the planet who do not know that the Earth is round and part of the solar system. It is not a secret that we live in a star cluster called the Milky Way, but not everyone knows about the monster that pulsates at its center. Recently, scientists obtained 100% proof of its existence. Let's begin by explaining what scientists have recently discovered. The galactic center of the Milky Way is an unusual place that is significantly different from the rest of space. This region, which is about 1,000 parsecs in size, is currently undergoing active star formation. It is also home to a monster that we will talk about today, and its name is the supermassive black hole in Sagittarius. But why has the world only recently remembered it? It's simple, it has recently become more active, unmistakably stating that it is very hungry. But how did astronomers detect its activity? Despite its massive size of around 4 million solar masses, the black hole at the center of the Milky Way is relatively compact, with a funnel diameter no larger than Mercury's orbit 44 million kilometers. Until now, it was considered relatively calm compared to its more aggressive relatives, as it had never before emitted deadly X-ray and gamma-ray bursts, which mercilessly obliterate everything for millions of miles around. Directly observing a black hole is impossible because even light cannot escape its fiery embrace. If you cross the event horizon of such a monster, no one will give their life for a broken penny to save you from the monster, and nothing can help you escape from the black hole at this stage. It is only possible to detect the black vortex by indirect signs, and it is complicated by the fact that Sagittarius A is a relatively small object, making its detection an extremely difficult task for Earth's equipment. In addition, the dense interstellar gas clouds obscure the black hole so much that if these gas curtains covered the familiar clouds in the Earth's sky, our planet would be in eternal night. Until 2018, attempts to see the gloomy vortex in detail had been made repeatedly, but the successes were insignificant, and only the strange behavior of stars around an invisible area was observed. To see the surroundings of the black hole in more detail, the Event Horizon Telescope project was created. It is a network of antennas operating in the submillimeter range and functions for a long time, but the results are not expected to be announced until the end of 2019. Recently, sensational information has been circulating about the movement of interstellar gas near Sagittarius finally being recorded. The information was obtained through a group of 8-meter optical telescopes with an interferometer called the Very Large Telescope, owned by the Chilean Observatory. The detected flares are clear evidence of accretion observed on the nearest stable orbit of a black hole. The location is relatively close to its event horizon and is a place where no earthly telescope has previously looked. Observations showed that the speeds at which the illuminated substance is carried around the black hole are staggering, reaching 3 times the speed of light, or around 100,000 kilometers per second. Astronomers observing this amazing phenomenon were truly amazed. To capture the signal from the Sagittarius black hole, which is currently on a diet, the observatory employed an innovative gravity system. The flares were discovered in July 2018, but it does not mean that accretion is currently occurring on a stable orbit of the black hole. It is possible that a century ago, the funnel swallowed an asteroid or a planet, and we only noticed echoes of this meal 100 years later. The main thing that was proven with the help of the network of Chilean telescopes, and in particular the super-powerful receiver gravity, is the fact of the presence of a massive black hole at the center of the Milky Way. It is currently dormant but could awaken at any moment. Unfortunately, our technological capabilities do not allow us to see the direct capture of a star or any other object by the black hole. In the future, if the improvement of the Event Horizon Telescope project and other similar missions continues, it may be possible for us to witness the dangerous neighbor's feast firsthand. By the way, it is believed that the black hole in this location is not alone. Japanese astrophysicists presented indirect evidence 2 years ago of another huge funnel 200 light-years from the center of the Milky Way. The mass of this black hole is much larger than that of Sagittarius A** and reaches up to 100,000 solar masses. What will be the next stage in the study of galactic monsters? Do you think attempts to observe the event horizon are not quite right? We are still far from it. The intermediate goal is to detect the shadow of the black hole. What exactly is hidden behind this romantic and at the same time frightening concept? In simple terms, it is a donut-shaped ring of hot gas surrounding the black hole and visible against the background radiation. Astrophysicist Subramanian Chandrasekhar once proposed an original method of identifying the silhouette of a cosmic monster. According to him, the black hole should be clearly visible against a bright white screen. According to the laws of physics, it will appear before the observer as an opaque dark spot. The effectiveness of this method is still in question, but research in this area continues. On November 22, 2014, the Assassin discovered an X-ray flash. Assassin is an automatic sky survey designed to search for supernovae. However, it discovered not a supernova but a signal from the center of the galaxy 290 million light-years away. Now, we believe that it was a star that got too close to the supermassive black hole, which has a mass 1,000,000 times greater than our Sun, swallowed a star and fed on it. This is the terminology used by astrophysicists to describe this process. Such events are very rare, occurring maybe once every 10,000 or 200,000 years. They are called tidal disruption events or tidal flares, when a star approaches one side of a black hole and experiences strong gravitational attraction while the other side experiences less attraction, which tears the star apart into pieces. The matter spirals and turns into an accretion disk, a ring of gas and dust that accelerates and heats up, emitting visible light as well as ultraviolet and X-ray radiation that we observe on Earth. What is remarkable about this event is that it turned a dormant, calm black hole into something we can now observe, all thanks to the matter that fell from the star. You might ask how we know what really happened there. I will explain how we know. At the very beginning, scientists prepared 3 X-ray telescopes to observe this part of the sky for many years aft. Can you tell us about black holes? Black holes are some of the simplest objects in the universe. They are characterized by only 2 attributes, mass and spin. There can also be a charge. Black holes must have a neutral mass and rotation, which can be easily determined by using Newtonian physics to measure the gravitational effects of black holes on other bodies. The mass of a black hole has been determined to range from several times that of our Sun to billions of solar masses, including supermassive black holes in the centers of most galaxies, including ours. What about spin? Black holes are formed from collapsing stars, and all known stars spin. Therefore, black holes must also spin. The chance of matter simply collapsing into a point without a collapse is slim to none. Any additional matter entering the black hole adds its own angular momentum, so black holes can spin quite rapidly. However, measuring rotation is more difficult because it only affects objects close to the black hole. There are 3 ways to understand it, all of which require understanding the most stable circular orbit. You can place an object at any radius and it will be stable no matter how close you get. This is not related to the general theory of relativity. There is an internal stable circular orbit with a radius known as r, which is the most stable circular orbit. However, no orbits are stable, and all of them fall into the black hole. Therefore, when you look at a black hole, the inner edge of the accretion disk is located at the radius of the most stable circular orbit. This radius depends on the rotation of the black hole. The faster it rotates, the smaller the radius becomes. Suppose the rotation is in the same direction as the material in the accretion disk. In that case, it allows particles to move closer to the black hole on the orbit. Rotation is usually discussed in terms of a dimensionless parameter that ranges from 0, no rotation, to 1, maximum rotation. However, I think you could also rotate to -1 if the black hole rotates in the opposite direction of the accretion disk. Now, as the rotation increases, the radius decreases by a factor of 6, eventually reducing to the event horizon. Many scientists consider this to be the maximum rotation a black hole can have, because if the minimum stable orbit were the size of the event horizon, light could escape from the black hole, allowing us to see the singularity. This is known as a naked singularity. There is currently no strong theoretical reason why a black hole cannot exceed this maximum rotation. We simply have not observed it. The idea of a naked singularity just seems wrong to most people. The maximum real rotation parameter is believed to be around 0.998. How can you use the radius r of a black hole to measure its rotation? First, let's think about how we measure the size of something far away from us in deep space. For example, the radius of a star. Most stars are so far away that they are simply point-like objects in our telescopes. So, how can we determine their radii? First, look at the spectrum of their light. By examining how the absorption lines are shifted, you can determine how far away the star is. The spectrum also tells us about the star's temperature. Now, the power radiated per unit area is strongly dependent on its temperature. So, if you know how far away the star is and how much energy is being radiated per unit area, you can determine its area, and hence its radius. You can do something very similar for the accretion disk of a black hole. Instead of estimating the radius of a glowing sphere, you estimate the radius of the dark disk in the middle of the glowing accretion disk. Then, you can use the radius r of the disk to find the spin parameter. It oscillates from 1/10 to close to the maximum, but this method only works if the study of the black hole is dominated by the study of the accretion disk. Often, this is not the case. Another approach is to consider the X-ray radiation emitted by iron around the black hole. Some black holes show a clear iron emission line, but instead of a single frequency that you would expect, the line broadens due to factors such as Doppler shift caused by the high speed of iron in the accretion disk and gravitational redshift caused by the extreme gravitational fields near the black hole. You can determine how close the black hole is using this method. By studying the fields near a black hole, you can determine how close the black hole was and thus calculate its radius, denoted by r. But what if there is no bright iron line emission? Fortunately, there is a third way, searching for periodic oscillations in the data, like repeating X-ray snapshots observed every 131 seconds. These cycles are likely caused by clumps of matter rotating around the black hole at high frequencies, very close to r, perhaps even half the speed of light. But what are these objects? Years before the tidal disruption, scientists hypothesized that a white dwarf would appear in orbit around the black hole, which could stably rotate in this way for perhaps 100 or 200 years. This would not be visible from Earth, but then another star was torn apart by tidal forces, with its mass falling towards the black hole and forming an accretion disk with added stellar debris. The white dwarf was covered in glowing material, creating a point of X-ray emission rotating around the black hole, and the period was directly linked to the rotation of the black hole. In this case, the measured rotation parameter was no less than 0.7 and possibly above the theoretical maximum of 0.09108, meaning that objects in the accretion disk move at least at half the speed of light. This is the first measurement of black hole rotation made possible by tidal disruptions, and it is suggested that this could provide a method for determining the rotation of inactive black holes, of which 95% we can get an idea of their rotation. Now, why is this important? Because it helps us understand the origin of black holes. If supermassive black holes grow mostly by constantly feeding on material from inside their own galaxy, we would expect them to have very high rotation since the momentum of that material would be more or less aligned. But if, instead, supermassive black holes grow by merging with other black holes, we would expect their rotation to be lower. As we measure the rotation of more black holes in different ways, we can better understand their growth. And since supermassive black holes lie at the center of most galaxies, they also lie at the center of our understanding of how those galaxies formed and evolved over billions of years.